Now that we've taken the time to explore some of these central tenets of quantum mechanics, let's start seeing how it actually helps us understand how matter is actually formed. And we're going to do that by exploring this idea known as the Bohr model of the atom, which is a simplification, but largely how we work with atoms today on the simplest level. Additionally, we're going to see how light interacts with matter through this phenomenon known as emission and this generation of things called emission spectra. So by about 1910, we started to understand a couple of key things that are going to lead to our understanding of how atoms are actually structured. So we already knew the basic structure of the atom by this point. We understood that there was a positively charged nucleus. We did not actually know there were neutrons, but I went ahead and drew them in here for just completion's sake. And we knew that we had these negatively charged electrons that were somehow orbiting a nucleus. This was known largely through experiments. We were able to determine some of these properties, namely that most of atoms were empty space that had this very, very dense nucleus at the core. But something else that we understood in 1910, or around that time, was that emission spectra of diffuse gases were one, discrete, and two, unique for different elements. Okay, so that's a lot of gobbledygook lingo, so let's start going through a little bit of what this means. So first off, what exactly is an emission spectrum? Well, let's say we have a diffuse gas, and by diffuse we just mean there's not a whole lot of it, in something known as a discharge tube. This is just a glass tube that contains some of this gas in it. And this gas is usually, for our sake, is going to be like a single element or single type of gas. So we're going to go ahead and say this is hydrogen, so diffuse hydrogen or H2 inside this tube. And we're going to run a current through the tube. And when we run a current through the tube, we excite the gas, and this is going to generate light. And we're going to start talking about why this occurs today, so kind of go with me here. But this light is emitted. For hydrogen, that light is kind of a pinkish purple color. And we are going to basically take this light and we're going to project it through a slit to get this light to be a little more collimated, getting it all going in one direction for one part of it. And we're going to put this light through something known as a spectrometer. And a spectrometer is usually made up of a couple of different things, including a diffraction grating. So remember, that is a lot like the two-slit experiment, except we have tons of slits. And that allows us to separate out the wavelengths of light. And then the light is then going to hit a prism, which is going to further separate them out and probably rotate the light to some degree, and we start having these individual wavelengths of lights coming out of the spectrometer. So the pink light that is emitted by hydrogen is actually made up of multiple wavelengths, or specifically multiple frequencies of light. And some of these are, one of them is red, one of them is a cyan, we have a couple of violets, etc. And then when we project this onto a screen or something dark, we get these very distinct colored lines, and this is known as an emission spectrum for this particular gas. So this is an emission spectrum. A spectra is just the plural of spectrum. So looking at hydrogens, for instance, this emission spectrum is discrete, and by that we mean there are very specific wavelengths, a specific number of them, that correspond to certain frequencies, etc. So looking at this, we've got our higher frequencies, lower wavelengths over here, our lower frequencies are higher wavelengths over there. So we have very, very specific lines. And these are going to be unique for different gases, or at least this was known at the time that it was unique for different gases. So this is hydrogen spectra, for instance, but we could also have other spectra, such as, for instance, this down here is heliums. Looks a little bit more like this, and when you combine all those colors together, heliums is kind of a peachy color, and then you've got underneath that neons, and neons comes off as a really orangey red color. But the thing is, though, is that even though you may not realize it, these ideas didn't really coincide. Our understanding of the structure of the atom with these discrete emission spectra, well, they didn't make a whole lot of sense together. Because when we look at an atom, so this is a very simplistic atom, let's go ahead and just say this is hydrogen, so we've got one proton and one electron. Well, when we have this electron orbiting the nucleus of this atom, well, it's going to be constantly accelerating towards the center. If we look at this from a classical physics point of view, it's moving in a circle, so it's a centripetal acceleration always towards the center of that circle, because that's a centripetal force always towards the center of that circle. It's being pulled by the electric force, but it's orbiting around with the speed v. But the thing is, though, is that we already knew by this point that if we accelerated electric charges, well, accelerating electric charges emit light. That's really how we get light. We basically cause charges to wiggle back and forth, and that constant speeding up, slowing down, changing direction allows light waves to form. So if this is the case, if this is accelerating, it should be emitting light. But light is energy. So if it's emitting a light here, well then that electron is going to lose energy, and it's going to start getting closer to here because it's not going to be able to maintain its speed and maintain the circular path. So it's going to start getting closer to the nucleus. It's going to then emit more light. Now this light is going to have less energy because originally we've been very high. Now we're getting to lower energy, so we're getting to like blues, for instance, and it's going to go even lower. And that's going to continue going as it spirals into the nucleus and eventually collides with it. So a couple of different things are happening here. One, we're going to expect to see a continuous emission spectrum for all matter, rather than what we do see, which are these very discrete spectral lines. Because, for instance, if I'm looking at this, well, if the electron is losing energy as it spirals in, it's going to emit purple, then blue, then green, then yellow, then orange, and red. All of that is going to basically go through a blur of colors before it eventually collides with the nucleus. So one, we should expect this continuous rainbow spectrum, rather than these discrete spectral lines. But additionally, and arguably more importantly, how can you even have matter this way? Because if we have a nucleus and electrons, and the electrons are spiraling into the nucleus, well, that's not a stable atom. And if we don't have stable atoms, well, that's a pretty big problem. And this is where we introduce Niels Bohr, a Danish physicist who published in 1913 this new model of the atom, this Bohr model of the atom, as it's often known, and which is the model of the atom that we largely use a lot still today to try to solve these conundrums that we were seeing with the fact that our, at the time, understanding of the atom with classical physics just did not make any sense. Alright, so how does this model of the atom work to try to solve these problems? Well, first, there's still a positive nucleus at the center, but then we have these distinct orbitals that the electron can exist in. And as long as the electron is in one of these levels, it is stable and it will not emit any light. So this kind of solves this problem that we're seeing, that one, as long as the electron is in these orbitals, it doesn't lose any energy, its energy stays constant. So if it doesn't lose energy, it can continue orbiting constantly, and also we're not going to get this continuous spectrum of light flooding off of the atom. Now the important thing to note here, though, is that each orbital coincides to a very distinct energy, meaning that the electron here has a certain energy, here it has a certain energy, here it has a certain energy, etc. But that tells us that, in fact, the energies of the electron are quantized. And this is actually the first quantum mechanical model of the atom. The electron can't have just any old energy because it can't exist just any old place. It has to only exist in these orbitals, and therefore can only have specific energy values. But how does this coincide with the discrete emission spectrum that we were seeing earlier, those very specific lines? Well, it turns out that the way we can think about this now is that electrons jump up to higher energy levels. The way they gain energy is by absorbing photons of light. Very, very specific photons, and we'll get to that in a second. And they jump down to lower energy levels by emitting very specific photons of light. So if I'm looking at a particular atom, and I'm looking at all of the wavelengths of light that it emits, well, all those wavelengths will coincide to differences in these energy levels, because you'll have the electron jumping down to this level, that would be a particular wavelength. This level, another wavelength. Jumping down to the bottom level, a third wavelength, etc. So all these coincide to very, very specific frequencies and wavelengths of light for very specific elements, and therefore we get this discrete emission spectrum. So let's go through a little bit of terminology just to make sure we understand everything. Obviously, we have the nucleus at the center, and we have all these orbitals, and what we call this very, very lowest level orbital is the ground state of the atom. We say the atom is in that ground state, and when the electron jumps up to higher orbitals, we say it is in an excited state. So the energy is increasing as the electron gets further and further away from the nucleus. In other words, the atom contains more energy, or the electron has more energy as we get further and further away. Additionally, we label all of these orbitals with something known as the principal quantum numbers. So the ground state we label as n equals 1, the first excited state is n equals 2, next one is n equals 3, n equals 4, etc. Now the thing is, though, is that drawing this Bohr atom can be kind of a chore, particularly if we're trying to do it quickly and accurately and we're trying to do some calculations, so we don't usually do this. Instead, we're going to utilize something different, which is known as an energy level diagram. So how you could think about this is I'm going to basically take a cutaway of this portion of the atom, of the electron orbitals, for instance, and I'm just going to rotate them a bit and flatten them out. So all of these dark lines here coincide to these different light pink orbitals over here on the left. Now something I want to note here is that if we look on the left, okay, these are separated out based on like the distance between the orbitals or something along those lines. And you notice that if I look at the energy level diagram, the levels at the top are much more closely spaced than the levels at the bottom. And that's actually because the separation of these levels is done proportionally to the amount of energy that the electron has in these levels. So there's a really big jump in energy from the ground state to this first excited state, a slightly less of a jump from the first excited state to the second excited state, etc. When you get up to these higher levels, there's barely any jumps at all between the excited states. So each level is an allowed energy for the electron. The electron can only exist on all of these lines. Imagine like it's like a ladder. The electron can only exist on the rungs of the ladder. It can't exist anywhere in the space in between. And additionally, the energy is going up from the ground state up to the top. We have our principal quantum numbers over here. And you'll notice that this top quantum number we write as n equals infinity. And what that really is telling us is that at that point, the electron has escaped the atom. It's got enough energy that it no longer stays here and it goes infinitely far away and is able to get away from it. So that is what that means. Now on the right-hand side, so we've got all the principal quantum numbers labeled here. On the right-hand side, we're going to put the energies, typically speaking, in electron volts. We're not going to usually use joules because we have very, very tiny numbers here. And you'll notice that the energy at the top one is 0 because when the electron is infinitely far away, there is no electric potential energy in the system. We have to remember that the nucleus is positive, the electron is negative, so as the electron approaches the nucleus, on its own, it would gain kinetic energy, but that kinetic energy has to come from somewhere, and it comes from the fact that we also gain negative electric potential energies, so that the total energy remains constant. So as we get closer and closer and closer to the nucleus, we're going to have more and more and more negative energies. Now, I'm going to go up and just put some values up right now just so you see what they look like, for instance, but this is just an example. This is not for any real atom. So for instance, in this one, the ground state would be negative 20 electron volts. The first excited state would be negative 12. Next one would be negative 8, etc. So to get out of the atom, for instance, the electron would need to absorb 20 electron volts. To get to this first excited state, it would have to go from 20 to 12. It would have to gain 8 electron volts, etc. So let's actually flesh that out in a little bit more detail. Let's say, and right now, what I've shown you right here is the energy level diagram for hydrogen. And hydrogen is often the one you see used in lectures and in classes because it's the simplest atom. So it's a real example, but we don't have to get into anything too gross mathematically. Alright, so I've got this here. And I've got, for instance, hydrogen's got multiple, it actually has more states beyond n equals 5, but they would be between this and the n equals infinity. These are the most prominent ones, and then n equals infinity, remember, is that escaping of the atom. So let's say, on this electron in the ground state of the atom, let's say a photon came in towards the electron that was 6 electron volts. Well, looking at these energy levels, okay, well, if it was at negative 13, if a 6 electron volt comes in, the electron is going to absorb it, and it's going to jump up to this first excited state, because there is a 6 electron volt difference between these two. But let's say we have a slightly different situation. Let's go ahead and say it's back at the ground state, and now let's say we have a 12 electron volt photon come in. So that's a higher energy photon, that's a higher frequency photon. Well, the electron will also absorb that one, and it's going to jump from negative 13 all the way up to n equals 4, which is negative 1 electron volts. So that is n equals 4, or the third excited state. But let's go ahead and do it one more time. Let's go ahead and say that we have a 9 electron volt photon come in. Well, now, nothing's going to happen because the electron, okay, so if we're at negative 13, if we absorb 9, we would be at negative 4, and we notice there is no energy level at negative 4 electron volts. And that means the electron cannot exist with that energy. It cannot stay that way in this atom. And so, it's not going to make this transition, and it's just not going to absorb that photon, and basically it's just going to ignore it, and the light's going to pass through the atom unhindered. It would just not be absorbed. So this is all known as absorption. The electrons in the ground state will absorb photons and transition to excited states. And the energy of the photon, though, must match the difference in these energy levels. And if they don't match, well, then it's simply not absorbed. The photon will not be brought in. Now, one thing you'll notice is I said electrons in the ground state. That's because if we have an electron that's already gone up to an excited state, we're going to see in just a second that it transitions back down extremely, extremely quickly. And because of that, it is statistically pretty much impossible for it to go from one excited state, get another photon, and jump up to another excited state in the amount of time required. So typically when we absorb, we go from the ground state and just jump up. Now, one thing you will also notice, though, is let's look right here. Well, to escape the atom, we would need 13 electron volts. So we had a 13 electron volt photon be absorbed by the electron. It would escape the atom, and then it would just kind of hang out, because it would not have any more additional energy. If it absorbs a photon with more energy than that, then it will take that additional energy and it will become the kinetic energy of the photon. So for instance, if it absorbed a 15 electron volt photon, it would jump up, escape the atom, but then if we had 15, we lost 13 to escape, it would have about 2 electron volts of kinetic energy for its movement at that point. So let's talk about then what happens once the electron is in this excited state. Well, when it's in this excited state, it's not stable, and it's going to pretty much jump down almost immediately to a lower energy state, and it's going to emit a photon. So let's say this one particular one's in the n equals 4 energy level, and let's say it jumps all the way down to the ground state. Well, that is an energy difference of 12 electron volts, so it's going to emit a photon that has 12 electron volts of energy. But let's say instead we're back here at the top, and let's go ahead and say that it first jumps down to the n equals 3 state. Well, when it does that, it emits a 2 electron volt photon, because there's 2 electron volts difference here, and then it can jump all the way down to the bottom, and that's going to release a 10 electron volt photon. Or it could take an even different path. Let's say it starts with that 2, but it jumps down to the n equals 2 state, and emits 4 electron volts, and then jumps down again and emits 6. So there are many different paths here, because emission is basically any of those are allowed. An electron from an excited state will almost immediately transition to a lower level energy state, one of them, and emit a photon in that process. And the energy of the emitted photon is equal to the difference in those energy levels. But the thing is that there are many different paths that this electron can take. It can go all the way down. It can skip states. It can skip some states and not others. All of this is basically at random, the sequence of it, and specifically the timing of how long each one takes. It happens extremely quickly, on the order of like nanoseconds, but this sequence is entirely random. It's entirely probabilistic. Now, oftentimes, though, we want to make sure we understand this to a degree, and specifically what type of light is absorbed or emitted, particularly if we're working with something like an emission spectrum. So let's look at this example. Let's say an electron is in the n equals 4 excited state like we drew here, and it transitions to the 3, then the 2, and then all the way to the ground state. And what wavelengths of light are emitted when this occurs? Now, we already went through this and showed that, okay, when it jumps down to this first state, that's a 2 electron volt photon emitted. The next state, it has a 4 electron volt emitted. Last state, to the ground state, it emits a 6 electron volt photon. But how can we figure out these wavelengths? Well, we know that the energy of the photon is equal to Planck's constant times the frequency, hf. And we also know that the wavelength of light is related to the frequency by the equation wavelength is equal to the speed of light over f. So I'm going to basically switch these out. I'm going to say that c over lambda is equal to f, and I'm going to plug that in right here. And we have hc over lambda, but I want to solve for wavelength, not for energy, so I'm just going to rearrange this. And we get that the lambda is equal to hc over the energy. Now keep in mind, I'm going to use Planck's constant here, and specifically the one of the electron volts, because the energies are in electron volts. So for this 2 electron volt photon, I'm going to use lambda is equal to hc over E. I'm going to plug in that version of Planck's constant, 4.14 times 10 to the negative 15 electron volt seconds, the speed of light, 3 times 10 to the 8th meters per second, over the energy, which was 2 electron volts, and I get a wavelength of 6.21 times 10 to the negative 7 meters, which we often write as 621 nanometers. You can leave it as times 10 to the minus 7 meters, but that's just another way to help us think about it. And we're going to do the exact same thing in the other two, except I'm going to substitute in 4 electron volts and 6 electron volts, and we would see that we would get wavelengths of 311 nanometers and 207 nanometers. So before we wrap things up, let's take 1 second just to discuss why can electrons only exist at these set distances from the nucleus? Why is the Bohr model, even though it's a simplification, why is it, for the most part, accurate? Keeping in mind that these set distances coincide to set energies. So we know that the energy is quantized, but why is that? Well, remember, we've talked about that electrons, when they're moving, they are quantum objects, and they can behave like particles, and they can behave like waves. So when they move around the nucleus, well, they're actually going to have some wave-like patterns. In fact, we can analyze their specific wavelengths using the de Broglie wavelength equation. And the thing is that when we do that, to form an orbital, basically what needs to happen is we need to have the wavelength of the electron form a standing wave that will basically loop back on itself. So for instance, if I start here at this point, it's going to go through a certain number of standing waves until it loops back on its point here. Now realistically, I did not draw this particularly well. The one in the middle would be one standing wavelength. The first excited state would be two standing wavelengths. The second excited state would be three standing wavelengths, etc. So if it doesn't match up in a standing wave, aka if we don't have like the wave connecting properly as it loops back around, well then that would not be allowed because that standing wave is not being reinforced. Now if we want to understand this a little more mathematically, we could just say, okay, well, the circumference here of this orbital would be 2 pi r, where r is the radius of the energy level, and that's just going to have to equal some set number of wavelengths of the electron for this particular situation, where that wavelength is a de Broglie wavelength and this integer n. So for the first one, n equals 1, would be 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, etc. Please note I didn't put any units on the wavelength and the radius here, but that's because they could both be meters, both be nanometers, etc. So what are our takeaways on the Bohr model and emission spectra of these diffuse gases? Well, one, can we explain why the Bohr model of the atom was required to properly describe the structure of the atom, keeping in mind that it allows the electrons to exist in these very stable energy states, and also explains why we get these very distinct spectral lines for emission spectra. Can we draw energy level diagrams, particularly for fairly simplistic atoms? Can we calculate the properties of light that are absorbed or emitted by a specific electron, therefore creating this emission spectra? And can we connect energy levels to the wave properties of matter, keeping in mind that these energy levels coincide to a certain integer number of the de Broglie wavelength of the electron?